All right, let's jump right into the explainer. Today we're tackling a topic that practically strikes fear into the hearts of anyone prepping for a coding interview: dynamic programming. If you've ever just stared blankly at a complex algorithm problem, feeling like you literally need a math PhD just to figure out where to begin, yeah, you're absolutely not alone. But today we're going to completely demystify this. We're breaking it down so clearly that you might actually start looking forward to these kinds of problems. Crazy, right?
The biggest trap? Thinking DP is just this giant encyclopedia of impossible to memorize mathematical tricks. It's really not. As this quote hits the nail on the head, DP isn't about memorizing formulas. It's about recognizing one specific pattern. Seriously, that's the big secret. It's just an intuitive pattern matching game. Once you know what that underlying pattern looks like, the whole veil lifts and the solution practically reveals itself to you.
So here is our roadmap to get you to that aha moment. First, breaking the memorization myth. Second, the two DP signals. Third, top-down versus bottom-up. Fourth, spotting the keywords. And finally, the master trick, defining state.
Okay, Section 1. Breaking the memorization myth. It is officially time to drop all your stressful preconceptions about DP. At its core, dynamic programming just solves problems by breaking them into overlapping subproblems and storing the results to avoid recomputation. Think about it. If I ask you, hey, what's 2 plus 2? You instantly know it's 4. If I ask you the exact same question a second later, you aren't going to count it out on your fingers again, right? You stored the result in your brain. You avoided the recomputation. DP is basically just teaching a computer to be incredibly efficiently lazy. We take a massive, scary problem, chop it up into tiny, bite-sized pieces, solve those tiny pieces exactly once, save the answer, and then just look it up whenever we need it again.
Let's move to Section 2, the two DP signals.
So how do we actually know when we're allowed to use this clever trick? Well, these problems are constantly broadcasting hidden signals, kind of like a secret decoder ring if you know what to look for. You're looking for exactly 2 signals, and when they flash together, boom, it's definitely time for DP. First up is optimal substructure. This just means the big, final optimal solution is perfectly built out of smaller optimal solutions. The second signal is overlapping subproblems. That means you keep bumping into the exact same smaller question over and over as you try to solve the big one. Let's look at a classic example question to really make this concrete. Think about the climbing stairs problem. Imagine you're climbing a staircase with n steps. Each time, you can either take 1 step or 2 steps. How many distinct ways can you reach the top? Well, to figure out how many ways to get to step 5, you perfectly build that answer based on the ways you got to step 4 plus the ways you got to step 3. That is your optimal substructure. But wait, if you calculate the paths to step 5 by looking at 4 and 3, and then you look at step 4 and realize it needs step 3 and step 2, hold on. You're calculating the answer for step 3 multiple times. Those are your overlapping subproblems right there. When you see both of these, DP is your absolute best friend.
Next up, Section 3, top-down versus bottom-up.
Once you've spotted those 2 signals, you've got to know how to actually write the code. We have 2 primary tools here, and they're really just 2 sides of the same coin. On the left, we've got the top-down approach. The technique here is called memoization, which, let's be real, is just a very fancy computer science word for jotting down notes in a cache. Its starting point is recursion. You start all the way at the massive final goal, like stair number 10, and recursively ask for the answers to 9 and 8, working your way backward. On the right side, we have the bottom-up approach. Its technique is called tabulation, meaning you're filling out an array or table step by step. The starting point here relies on your base cases. So instead of starting at step 10, you start at step 1, then step 2, then step 3, building the blocks iteratively from the ground up until you hit 10. And each cell you fill out depends only on the ones you just securely filled out right before it. Honestly, for most people, top-down memoization is going to be the most intuitive way to kick things off in an interview setting. Let's map out the logical steps so you can literally visualize writing this out. Step 1, write the basic recursion first. Seriously, don't even worry about optimization yet. Just get the brute force recursive logic down. Step 2, add a cache. Just pass a simple hash map or dictionary into your function parameters. Step 3, at the very top of your recursive function, drop in an if statement. If the answer for this specific subproblem is already sitting in the cache, just return it instantly. Step 4, if it's not in the cache, compute it. But right before you return that answer, save it into your cache for next time. It is literally that simple. This tiny trick transforms a solution that would normally take a computer millions of years to run into something that finishes in milliseconds. It's a total game changer.
Moving on to Section 4, spotting the keywords. Now that we've got the mechanics down, let's talk practical cheat codes. Interviewers are almost never going to just hand it to you and say, hey, use dynamic programming for this one. Nope. They hide it behind very specific phrasing. When you're reading a problem, alarm bells should be going off in your head the second you see words like maximum, minimum, number of ways, or can you reach? Like, find the minimum number of coins needed. That's the classic coin change problem. Or going back to our example question, find the total number of ways you can climb the stairs. Spotting these keywords rapid fire is your absolute first step. They're basically neon signs flashing, pointing you right to DP.
The second you spot one of those keywords, there is an absolutely crucial mathematical question you need to ask yourself immediately. Can the problem be expressed as f of I equal to some function of f of I minus 1, f of I minus 2, and so on? Now, in plain English, that just means, can the current state you're trying to figure out be calculated strictly by looking at the states that came right before it? In our climbing stairs example question, the math to get to step I is literally just adding the answer from step I minus 1 and step I minus 2. If you can map the problem to this kind of mathematical relationship, congrats, you've completely validated that DP is the way to go.
And look, if you're feeling a bit overwhelmed, just remember these classic hits: Fibonacci, climbing stairs, coin change, longest common subsequence, and the 0/1 knapsack problem. I know packing a virtual backpack sounds wildly different from making change at a cash register, but I promise you, they all fall to the exact same formulaic approach we just went over. Every single one of them has optimal substructure, they all have overlapping subproblems, and they can all be solved by caching previous states. Master just one of these, and you've basically unlocked the architectural blueprint for the whole shebang.
Finally, Section 5, the master trick, state.
We have arrived at the final and honestly most critical piece of this entire explainer. The real trick to DP is defining the state clearly. You should absolutely spend more time on that than on typing out the code itself. But what actually is state? Well, the state is simply the set of variables that uniquely describe a specific subproblem at a specific exact moment in time. In our stairs example, the state was super simple, just one variable, I, the current stair we were standing on. But in a problem like 0/1 knapsack, it's two variables, your current index in the list of items and the remaining weight capacity of that backpack. The absolute master key here is stopping yourself from rushing straight to the keyboard. Take a breath, grab a whiteboard or piece of paper, and ask yourself, what exactly does my state represent in plain English? I guarantee you, once you vividly define your state, the coding part becomes trivial. The logic will literally just write itself around the state you've defined. As we wrap up this explainer, I really want to leave you with a question to chew on for your next coding interview or personal project. The next time you're staring down a horribly complex problem, are you going to try to frantically memorize 100 different solutions? Or are you going to take a step back and look for those overlapping subproblems? The pattern is out there, right in plain sight, and you've now got the exact tools to find it, break it down, and completely optimize it. Thanks so much for joining me today, and keep your eyes peeled for those patterns.